Yeah. I'm sorry about that. I should have said that. So welcome everyone to the second week of the Stefanich-Tannaka book. We'll be talking about categories. So Giovanni, please take it away.
Okay, so hello everyone. The goal of today is to introduce Grothendieck and Prestable and Grothendieck Prestable categories, and like by categories I will always mean infinity category. Two things. The first one, if you don't hear what I say, like ask me again. Like online meetings are very hard to do. And the second one, yesterday I had another seminar and they told me that my handwriting is very bad, apparently. So if you don't understand what I'm writing, ask me. So I would like to start with the definition of pre-stable categories. I will not like motivate at all what we are going to do. I think in the next talks we will see why these things are useful. But in any case, like the main motivation that we have in mind is that like often we have a geometric object, we can form some infinity category, stable infinity category of quasi-coherent sheaves over it, and often we have a T-structure, so like a way of like seeing things concentrated in positive and negative degree. And pre-stable categories are always like they try to capture what a T-structure is essentially in more like less behaved situation. So definition. C category is pre-stable if pointed. So we have an initial and terminal object and they coincide. The suspension functor is fully faithful. And free, whenever we have a span of the form 0 to the suspension of something, then we can complete this square to a pullback square. To a pullback, which is also a push out. So these squares are bicartesian. Not every square is bicartesian, but these are. And okay, like very simple examples. First of all, if C is stable, then like it's clearly pre-stable. And these are like some degenerate case. Like when we study pre-stable categories, like this fact that every stable category is pre-stable, it's not very pleasant, I would say.
Sorry, one short question maybe.
Yeah.
I think you might be missing the existence of some colimits. I think you need finite colimits to exist.
When you have like true, and finite colimits, let's say. Otherwise, the push out does not make sense.
Yes, exactly. And like you can't define sigma.
Yeah, true. Second one, if C is stable and we have a T structure, so a pair of full subcategories which satisfies some condition, like they are kind of orthogonal and stable and under its suspension and the suspension, and like every object fits into a fiber sequence where like the fiber it's in positive degree and the cofiber it's in shift and negative degree. Never mind. Then the connective island it's pre-stable. Yeah. And it's also very interesting because this like thingy, it also has finite limits. And in fact, this is almost a characterization of like pre-stable categories with finite limits. And to see that, like remark, let me recall that like we have two types of stabilization. Like we want to show, what we want to do now is to show that every stable category with finite limits can be characterized, is the connective island isle of like a T structure. So, and to do that, let me recall that we have a functor call it the Spanier-Whitehead stabilization, which goes from categories with finite limits to stable categories, which is given by like stabilizing under suspensions. So we have the suspension factor, and we can stabilize along the tower given by suspensions. These functors comes equipped like it's the left adjoint to the inclusion of stable categories inside the category with finite colimits, and we have a map from C to Spanier-weighted stabilization of C. Let's call it Rho, which essentially like puts everything in the first component and then suspended. Which is right exact. And this is the unit of adjunction. Okay, with this thingy, we can prove the following lemma. So let's assume that our category C is pointed with finite colimits. Then the following are equivalent. One, C is pre-stable. And let me do another thinking before. Yes, I would like to prove another thingy. So like the first observation is that in terms of the Spanier-Whitehead stabilization, we can rephrase the second condition. So the suspension being fully faithful. So 2, the suspension is fully faithful with 2 prime, which says that Rho from C to the Spanier-Whitehead stabilization, it's fully faithful. And 2 second, there exists Rho from C to D, where D is stable, and Rho is colimit preserving, finite colimit preserving, and is also fully faithful. Rho is fully faithful and colimit preserving. Finite maybe. And the proof, it's immediate, like it's clear that 2 prime implies 2 second. And it's also clear that 2 implies 2 prime, yeah, by essentially construction. Not obvious. And for 2 second implies 2, we note that we have a diagram since Rho is exact, given by C, C suspension of C, Rho D, suspension of D, which commutes, and yeah, this, like the vertical maps are fully faithful. Sigma D, suspension of D is fully faithful because it's D is stable, and yeah, it implies that C, suspension of C is fully faithful. Yeah, and like before going on, let me point out that like these type of statements will like always often appear in the context of pre-stable categories, because like pre-stable categories always admits an intrinsic and extrinsic definition, and this type of lemmas, this type of results allow us to move from one thing to the other. So prop, which is connection with the structures, connection. So, yeah, C category. The following are equivalent. 1, C is pre-stable with finite limits. 2, C is pointed with finite colimits. And the canonical map, the unit of the adjunction that we saw before, from C to the Spanier-Whitehead stabilization is fully faithful and exhibits let's say C as the connective island of a structure for the structure on C, structure on the Spanier-Whitehead stabilization, and free, like the basically two, but like without saying that we are working with the Spanier-Whitehead stabilization, there exists D stable plus at the structure and an equivalence with C and the connective part. And yeah, the proof of these results, like always, like the second condition implies the third one, it's okay, because yeah, we can take D to be the Spanier-Whitehead stabilization. We can also easily prove 3 implies 1. This is by the example before. So like the hard part is always going from like the extrinsic definition to the intrinsic one. So sorry, did I put it correctly? Like 3 implies 1, yes. So we have to do 1 implies 2. Sorry. Okay. Yeah, of course, C prestable, so it's pointed with finite colimits, and we have the map Rho by lemma. Since it's fully faithful, we conclude that Rho is fully faithful. Okay, so at least there is the hope that C is equivalent to a full subcategory of the Spanier-Whitehead stabilization, and therefore we define the Spanier-Whitehead stabilization to be spanned by the object P of X with X and C, so that this is canonically equivalent to C. And the Spanier-Whitehead stabilization in degree, or in positive degree. Yeah, like we have to check that this thing is at the structure. And yeah, this is a computation by defining the Spanier-Whitehead stabilization in degree negative to be those Y in the Spanier-Whitehead stabilization, such that Y is equivalent to rho of omega n for, no, sorry, because it's better to do it in this way, omega n rho x for x in C and truncated. Yeah, and then one checks that this is indeed a structure. And like it would be seems a little bit strange that like we have this condition. I think there is a pointer here. Like there is this condition of being n truncated, but like by checking like orthogonality, for example, one immediately sees that like it's required to have the connective and the shift, the negative shift of the non-connective part to be orthogonal. Like you need that thing. So yeah, I don't want to prove it because it's like a very long and tedious proof, and there is actually nothing that we can learn from it. Yeah, the observation is that okay, this is a very nice characterization of pre-stable categories with finite limits, because we are often like reduced to study stable categories with a structure. But let me note that point 2, it's not the best, like it's not the only approximation of C that we can have. I mean, it's not canonical. Let me state it in a remark. So C prestable with finite limits. Then, okay, we have seen that there exists such a stable infinity category D with a structure and an equivalence between C and the connective part. What I claim now is that, okay, we can take the spectrum objects of C, and this is defined as the limit over this diagram, where instead of like stabilizing by using the suspension, we stabilize using the omega function, the loop functor, is stable with a structure, and is equivalent to C. In particular, yeah, like we see that the category D in the in the statement of the lemma before, like sits in the middle between the Spanier-White stabilization and the this like taking spectrum objects of our category. The category D in the sense that, like, yeah, the Spanier-White stabilization identifies with like the right completion of sorry, with the like bounded below part of D, of the T structure on D. So, and yeah, this is included in D, of course. And yeah, and we have a map to the right completion, which is equivalent to the spectrum objects of C. And this is called the right completion. So in particular, it's defined as the limit over this diagram. So we have, let's say, D minus 1, D minus 0, and so on. And here we have the truncation functor. The proof of this statement, so there are two things that one has to check in this construction. So like this equivalence here and this equivalence here, and they follow since the structure on spectrum objects is right complete, and like this one follow, and also by the fact that like the category D in the statement of the proposition add connective part equal to C, and in particular, this also implies that we have this equivalence. So yes, there is no canonical choice. And like often actually one uses taking spectrum objects, especially when we go to things which are big in the sense of like presentable categories, which is what we do now.
Sorry.
Yeah, sure.
I think the right map from D to the spectrum objects on C will in general not be an inclusion.
No, in general, no.
I don't know what some.
No, there are conditions for it to be an inclusion.
I don't know. I mean, maybe probably if it's already right complete, but I mean.
I'm thinking about example, and in general, it's not like an inclusion.
Mm-hmm. All right. I just wanted to know that. Okay.
Yeah, I'm not so sure in this moment. Let's say it could be. I'm not sure.
Yeah, I don't really know.
With schemes,
I don't
know.
It's fine. All right, thank you.
So let's pass to the big variant. So Grothendieck Prestable. Okay, definition. The category is Grothendieck Prestable if one, it's prestable and presentable, and like this is not enough. The real condition is that filtered colimits are left exact. And yeah, let me remind what it means. For every I small filtered category, the colimit functor is left exact. Or equivalently, like if you fix a small category, a finite category, and you consider the limit functor, that functor preserves filtered colimits. The same. So yeah, again, we have a way of going from this intrinsic definition to an extrinsic one. So lemma. Let's say that C is presentable. The following are equivalent. One, C is Grothendieck Prestable. Two, C is prestable. And yeah, the loop functor, which is a limit, commutes with filtered colimits. Three, the same, but with the infinite loop functor. And four, yeah, we can find a presentable stable infinity category, not a structure, and an equivalence, but there exists the presentable stable with the structure compatible with filtered colimits and an equivalence which identifies C with the connected part. And like, if you don't know what the structure compatible with filtered colimits means, it appears in the proposition, in the proof. So let's wait for a moment. Okay, condition one implies two, it's trivial. Yeah, because like the loop functor is a finite limit. And 2 implies 3, for example, it's also trivial. Yeah, since we take, like, it's a definition of spectra, essentially. So it depends on how this thing is constructed and, like, so let's say by construction, it's better. And of course, 4 implies 1, sorry, 3 implies 4. Let's do it in this direction. if C is pre-stable, we can take D to be the spectrum objects of B, of C. Take this as a T structure, a canonical T structure. Where spectrum objects of C are in degree positive are defined to be those spectra on C such that the underlying space is contractible. And yeah, since omega infinity is compatible with filtered colimits, it follows that this is the right thing. Okay, so the real problem is to prove 4 implies 1, which is that we have this prestable category with all of this presentable stable category with all of this problem, and we have to check that C is prestable. Since we already know that if C is equivalent to the connective objects of D, then it's prestable. The real thing is to show that it's presentable and Grothendieck. Presentable and filtered colimits are exact. So since and okay, so to do that, we don't show that whenever I have a small filtered category, the colimit functor preserves is left exact. We do the contrary. So take K to be finite category. And consider the limit functor from functors from K to C into C. And to show this preserves commutes with filtered colimits. But now what we can do is to note that like this diagram commutes. So we have fun K C, which I recall you it's equivalent to the connective part of a T structure on D. This is the limit functor. And what happens is that here we can include into D. We can consider the limit functor to D. And here we can truncate. So sorry, let me put it in this direction because the diagram yes. Where here we have the post-composition with the inclusion of the connective part, and here we have the truncation. And now we are done because like this functor commutes with filtered colimits because the inclusion is a left adjoint. This functor commutes with filtered colimits because finite limits in a stable category are the same of finite colimits, so they commute. And this functor commutes this. You don't see that? Okay. Wait. Sorry. I'm a bit incapable of using this thingy. This functor commutes with filtered colimits because it's the definition of being data structure being compatible with filtered colimits. So and so we are done. And let me specify that So this concludes the proof, which is very nice because like at this point we have another extrinsic definition of being a Grothendieck prestable. Okay, maybe some examples. Okay, always the degenerate one. So if C is presentable stable, then we know that C is prestable. So C is sorry, like let me phrase it in another way. C prestable, sorry, C stable category. Then we know that it's prestable. And yeah, you can use the proposition or equivalently like the argument that I gave before. C is Grothendieck if and only if it is presentable. Another example, which maybe it's more interesting because it's like one that appears a lot in like application. If C is prestable, sorry, and compactly generated, so C is equivalent to the incompletion of some small category D, then it's Grothendieck prestable. Why? Because in a compactly generated category, filtered colimits are always left exact. And like how you do that, how do you prove this claim? You use like compactness. You reduce to checking on compact objects and then it's triggered. Example in application, like if A is an abelian category, then like there is a way to construct D of A, which is the derived infinity category of A. This has a structure. D of A greater or equal than 0, D of A in negative degrees, and which is right complete. And compatible with filtered colimits. Maybe Grothendieck abelian, sorry. And one can deduce in particular that D of A in positive degrees, it's Grothendieck. Yeah, and then there are like many other examples in this direction. I don't know, you have a stack, you consider the derived category of quasi-coherent sheaves on it. You look for the T-structure and yeah, well, this structure is always right complete and compatible with filtered colimits. So yeah, you end up with something which is Grothendieck stable most of the times. Okay.
Sorry, quick question. In the first example you gave, the first example you had?
Yes, this one.
How did you get compatibility with filtered colimits there?
Like because you have to check that finite limits commutes with filtered colimits. So you do essentially the same step that I did here. You use that like limits in a stable categories are the same of colimits and they commute with filtered colimits.
I see. Thank you.
Yes. Like this is an example. Like it's somehow a degenerate behavior. Like stable categories like are a subcategory of Grothendieck prestable categories, like in derived things, and they are a very degenerate example. And like you can make this claim precise, and I think we will see it in the next talk. So, yeah, what we have to do is to study morphism of Grothendieck prestable categories. So definition, we let Groth, this is not a Groth, to be the full subcategory of PRL spanned by Grothendieck Prestable categories. And what I said before, that presentable and stable, it's a full subcategory of Groth. Yeah, let me put some dots to say. Okay, yeah, what we can do now? Like the first thing is that like Grothendieck, this category admits a very like explicit description when we apply this as the spectrum object functors. So let's say prop. Let's say that C and D are Grothendieck Prestable. Then, okay, we can consider the internal object between them, and we can map to the stabilization. Let's call this map theta. Then this map is fully faithful. And like we have a description of the essential image, the essential image, is given by F which is colimit preserving and right T exact. And now I remind you what it means. Okay, like in other terms, this functor is a functor of two categories, which is locally fully faithful and essential image, it's whatever it is. Like, let me remind you what this means. First of all, when I write spectrum objects of C and spectrum objects of D, I always mean that I pick the canonical structure, so the one that is right complete and compatible with filtered colimits. And yeah, a functor F, it's right T exact if like the connective part is sent to the connective part. And like the proof of this fact, yeah, follows by writing C. Yeah, spectrum objects at the level of presentable categories, it's in PRL, it's defined as a colimit, but we can still write C as the, yes, as a colimit, so lim. Sorry, what am I writing? Okay. Blah, blah, blah. And yeah, what we can do is to like apply follows by noting and applying fun L blank spectrum objects of D to deduce theta is equivalent to the following functor. So like we apply this thing, we take out the limit, we get a diagram, and like what are the maps of this diagram? They are given by precomposition with the suspension of C, by functoriality. Yeah, but colimit preserving functor commutes with suspension, so these maps can be described in terms of the suspension of D. So which are always equivalent, so the diagram collapses. So the map fun L C to spectrum objects, sorry, from speed D. which is given by I take a functor f, let's call it little f maybe, and we send it to f composed with the infinite suspension of d. And like then it's clear that this functor is fully faithful, theta prime, let's say. And that the essential image is given by what I said. Yes. Okay.
Sorry, what does the superscript L mean again?
Okay, I use it in the wrong, like in the wrong context. Pan superscript L means functors which are left adjoints in general. And
Okay.
I identified with colimit preserving functors.
Okay.
Because, yeah, you know, adjoint functor theorem. Lurie does it on the contrary, like it says that colimit preserving functors are instead given by putting an L here, for example. I don't like it, so. Okay. Let me give a remark, which is one of the computation, like a kind of a computations that I always, when I have to work with these things, I always do, and like I have to think, okay, is it correct or not? So let's say that we have FL from C to D in Grothendieck. So this is a left adjoint. Which means that yeah, we have FL adjoint to FR. Yeah, then we have the following diagram, C, FLD. Here we can go with the suspension of C to spectrum objects of C. And here we can go with the same functor. And we have the spectrum objects of D. And here there is the functor big FL, which is defined as the suspension, the spectrum objects functor of FL, little FL. And this is a notation that I will use in the following. So yeah, it's important. And this diagram commutes. Now, in particular, one can pass to right adjoints. And therefore, we get a diagram of this type. FR, here we have the underlying space. And here we have FR, big FR, and this diagram commutes. But remark, which is important, FR, it's not the spectrum objects of little FR. Yeah, this is, yeah, it's not even possible to make sense of spectrum objects of a functor which is not of FR, for example. Yes. In any case, remark, we always have a map okay, so like we can use the above diagram to construct the following map. What we can do is construct a comparison map between little fr and big fr. So this is the map that we want. Indeed, . we can use the co-unit of the adjunction on the co-unit. To construct it. Let's say it's C as comparison map. Yeah, like you have this co-unit, you apply FR, and yeah, you're wrong. So what I want to say, like in this case, is that even though FR it's not given by spectrum objects of little FR, if the target is Grothendieck Prestable, if D is Grothendieck Prestable, then this map is an equivalence. Claim. Yeah, and we are in the assumption that D is Grothendieck, like I wrote in them here, but. Yeah, I don't want to write the proof because like it's there are two equivalent ways to see that depending on how much you want to write. The first one is like you can write the OM adjunction, like an adjunction between OM anima and like move all the functors to get that FR it's equivalent to this thingy. But this works only if we note that this is an adjoint equivalence. Why? Because we can use by lemma, and I have to go a little bit up to see which lemma I mean. By this lemma here. And like to do that, you need point free. So maybe by in particular, we can prove the claim by playing with adjunctions. Sorry, I made a mistake. Here there is a little, we have to restrict to connective objects. At a certain point, you will end up having like an OM anima where you have a suspension of like infinite suspension of D applied to something, infinite suspension of D applied to something, and then like you that OM anima is computed in spectrum objects of D greater or equal than 0, but then like you use the suspension factor is fully faithful to reduce to D, and then you're done. So this is very nice to know, like that. Okay, I don't know how to construct the big right adjoint, but I always know that I can like go down to compute the small right adjoint. So yeah, like what we have to do now use this fact to move properties on FRL or FR to big FL and big FR. And like the first one, lemma, let's say that we have such a functor, then the following are equivalent. The first one, FL is left exact. And this happens if and only if it sends truncated objects to truncated objects. And free, FL is, so let me remind you that this goes from spectrum objects of C to spectrum objects of D, is left T exact, which means, yeah, FL of spectrum objects of C less or equal than 0 goes into spectrum objects of D less or equal than 0. So proof. Yeah, these lemmas are always like a little bit boring, I would say. Like, it's the right things that you will expect. So let's go a bit fast. Okay, 1 implies 2, it's always true. Because like if you have a category with finite limits and you have a limit preserving finite limit preserving functor, then it sends 0 truncated objects to 0 truncated objects. It's always true. And our categories are presentable, so they have finite limits. Let's do, for example, first 3 implies 1, which is the other implication, which is easy. Yeah, we have identified the Spanier-White stabilization of C with the spectrum objects of C, the bounded part, bounded below, bounded above, bounded below part inside the, and this is, I'm sure that it's an inclusion. It's an inclusion. So I will I think also the other one is an inclusion then, to answer Alex's questions. I'm sure that this one is an inclusion. So, yeah, what we can, we have this identification. Moreover, we know that big FL is, since it's a left adjoint, is always right T exact. And by our assumption, by free, it is then T exact. And hence it restricts to a functor from F little fl restricts to a functor between the Spanier-White stabilization, as you can see from the formula. And this functor is exact, T exact, with the T structure induced. And yeah, it's not easy to see, but it's a computation that you can do by this implication by unbundling the definition, that this implies that FL is left exact. So we have proven that 3 implies 1. The hardest part is 2 implies 3, for example. And let me say some words. Yeah, it follows by right completeness. Of spectrum objects of C. So what you do is take an object in the negative part, you have to see that it's sent to the negative part of D, of spectrum objects of D. You use that the structure on C is right complete, so you can write it as a limit of its truncation. FL commutes, big FL commutes with filtered colimits. So you can reduce to something which is bounded on one side. And yeah, then you play with exactness of the fiber sequence, like you can do by induction then, and like you play on the fiber sequence that defines the like truncation, and the last term of this fiber sequence is always discrete, and then you use that to perceive discrete objects. To reduce, it's the trick that one does when you have right completeness. Okay, and yeah, in particular, we get a subcategory, Grothendieck Lex, subcategory of Groth, which is not full. Okay, let me call left exact functors in the sense that big FL is left the exact. And yeah, I think I will change a little bit my plan, but yeah, the first result that I'm not gonna prove, it's a result on limits, which says that Groth Lex admits finite limits which are preserved by inclusion. So in particular, whenever you have a diagram, you can compute the limit in presentable infinity categories, and then you're done. Yeah, AG example, it's C alpha is a diagram in such thingy. With limit C, then the spectrum objects of C are essentially given by the spectrum objects of, by the limit of the spectrum object on C alpha. And yeah, like and in particular, we can move to the T structure to get the limit of our diagram. So yes, and hence an object is connective if and only if it is on every C alpha. Okay. Second property, it's like also let me note that in general this category Grothendieck Lex does not admit finite colimits. Yeah, I think the problem it's the same that one encounters with one categories. So like some behavior on p-adic complete things. Okay. Now we move to other properties.
Is this example like, does it follow from the proof or is it obvious? I don't
know. No, it's not obvious. Absolutely not. From the proof of the proposition, yes.
Okay.
Yes. It's exactly what you do. You define the limit to be that thingy, and then you check that it's Grothendieck Lex.
Okay.
Okay.
Maybe also one remark on why you might not have colimits. I mean, somehow being left exact is some like coherence property with respect to limits. So somehow,
yeah, it's
assume that maybe like limits are more more amenable than colimits. But yeah.
Yeah, like if you want like a naive definition, when you have a scheme, quasi-coherent derived category on that scheme, and you have a T-structure on that thingy, like you always expect that an object is connective if and only if, like, when you pull back to the connective, like to affines that thingy is connective. So,
no, I was just talking about the proposition that why you might not have finite colimits in this category.
okay.
I mean, it's because like you're mixing limits and colimits.
Yes.
I mean, that's just like my stupid sort of intuition for this. But yeah, okay, thanks.
So proposition FL from C to D in Grothendieck. The following are equivalent. One, FL is compact. And compact here means, by definition, that FR, so the right adjoint, preserves filtered colimits. And if you're interested in Grothendieck duality or like dualizable things, this is like a very important property. Second, FR, which I remind you is the right adjoint to FL, big FL, defined as the spectrum objects of little FL, preserves small colimits. Proof of this fact, okay, we know that the composition D, suspension of the spectrum objects of D, FR, big FR, to the spectrum objects of C, loop functor, it's equivalent to little FR. So let's consider, for example, that 2 implies 1. We know that big FR commutes with small colimits. Okay, let me do this. This one commutes with small colimits. This one is a left adjoint, so all colimits. So this composition with all colimits. And like C is Grothendieck Prestable. So this functor, by like the characterization of Grothendieck Prestable, commutes with filtered colimits. And we deduce that the composition commutes with filtered colimits. Okay, and yeah, well, in 20 minutes, I don't think I can prove like the other implication. But like, let's see some words. Like, again, when you have to go down from spectrum objects to like the category, what you have to do is to play with like right completeness. And let me just give a sketch of how you do that. So we have to prove that a little FR preserves filtered colimits. What we know is that FR is exact because it's a right adjoint between stable categories. So to show it preserves filtered colimits, because a functor that preserves colimits and filtered colimits, finite colimits and filtered colimits, preserves all colimits. Okay. So how many details I want to give? Not that much, not that many. So idea, define G of n of x to be the right adjoint big FR truncated, precomposed with the truncation. So Gn is a functor from spectrum objects of D to spectrum objects of C. And by right completeness, one deduce that the canonical map from Gn of X to Fr of X is an equivalence. Yeah, you play with like the exact sequence, and yeah, you use also that R is left at the exact, being a right adjoint. And then we do the same argument again for M. We define Gmn of X to be the truncation of Gn of X. So this is the truncation of Fr truncated X. And like again, one plays with right completion to get that this functor approximates this object, like evaluated at X approximate these objects. Then which we have seen that's equivalent to F. Okay, so what like it's now sufficient to check that Gmn commutes with filtered colimits. So with filtered colimits. And by shifting, one can reduce to the case where both indexes are 0. Okay, but G00, it's defined. One can check that it's equivalent to do the suspension of C composed with little fr, precomposed with the loop space only. And this functor preserves filtered colimits by assumption because Fr does. Yeah, like omega B, that like this functor preserves filtered colimits because it's a left adjoint. This one by assumption, and this one because like B is Grothendieck. So, and this like concludes the thingy. In particular, as before, we can like construct the category on these objects. Did I put a remark or something? No, sorry. So we get Grothendieck with compact morphism, subcategory of Groth. And proposition, which again I will not prove because it's like complicated. Groth admits small colimits. Preserved by the inclusion in Groth. Okay. And yeah, like you essentially can do the same example as before. You take a diagram, you compute its colimit, you take spectrum objects of it, spectrum objects like take out commutes with that colimit, And so, yes, you play with connective things to in this case, to the co-connective things to get the right category. Yeah, it's not really important. I mean, it's hidden in the proposition. Okay. So one last example, like one last property, which is really related to compactness, but it's like a more specific version of it, which happens if you're interested in, for example, pseudo-coherent or complexes on a scheme, or almost compact objects on a stack, which are essentially the same. So let's take FL from C to D in Grothendieck. And we say that FL is almost compact if FR preserves filtered colimits of n-truncated objects. F from the truncation, this does not, from the truncation of D at the level n to C preserves such things. And let me note that this D of less or equal than n is not the T structure. There is no T structure on D. D is not stable. It's pre-stable. But somehow, here is where the notation collides, between topos theory and homological algebra. So yeah, remark, this is not a T structure. Yeah, lemma.
So it's truncated in the topos theoretic sense, right?
Yes, exactly. So it's truncated if for every other object you compute the anima, and that's gets you an n-truncated anima. And n-truncated here means that the homotopy groups vanish in degree n+1, from n+1 and above.
I would think that this is, I mean, you can put a T structure on the spectra, and then this will exactly be the
yes, but D is only pre-stable, so no T structure. Lemma. So if we have a morphism in Groth, the following are equivalent. Okay, 1, FL is almost compact. 2, FR preserves filtered colimits when restricted to a functor from spectrum objects of D to spectrum objects of C. And 3, the same but with a shift. Yeah, one says, why do you need this thing? It's clear that 2 and 3 are equivalent. Yeah, it simplifies a lot to the proof. So proof, and this is the, basically the last, how many minutes do I have? 10. Okay, so let's be quick. 2 and 3 are equivalent, yeah, since FR is exact, essentially. And yeah, spectrum objects of D shifted by n, this is the same as suspension with a minus, well, probably a minus, but I never remember, less or equal than 0. I will say a plus, we are homologically. So like, let's do 3 implies 1, and let's black box 1 implies 3. 1 implies 3, it's essentially like you have to play a game with right completeness. So we assume that FR preserves filtered colimits were restricted, and we have to show that little FL is almost compact. So the right adjoint preserves filtered colimits on truncated objects. So like we pick X from E to D less or equal than 0, then filtered diagram. Yeah, and one computes FR of this colimit. Yeah, by the way, it is obvious that the colimit exists in D less or equal than N. So there is no condition to put there. Okay, like we know again that FR it's given by the loop functor on C, infinite loop on C, big FR and suspension of D. Yeah, and then like one plays with a lot of equivalencies to get that this is the same as the colimit of FR of X. And in one of these equivalents, let me say then, since in one of these equivalents, one has to use that we land in the right category. So then okay, and the other properties are like, because we are playing with the joints with the right properties. So 1 implies 3, again by right completeness. Yeah, let me black box it. So, but it follows by right completeness. And proposition, which is the same as before. Groth AC, subcategory on almost compact objects. Functors as finite colimits, small colimits, sorry. Preserved by the inclusion. Okay, yeah, and like the usual example, yeah, if you have a diagram in Grothendieck with almost compact functors, you compute the colimit inside the Grothendieck categories. You take spectrum objects of these things, colimit pulls out of the spectrum objects, and you look at the connective part again to get your thing. Okay, let me conclude with like one properties that it's useful, will be useful in the following seminars. Let's say 4, commutation. So let's say proposition. EJ small categories and F from the product to Grothendieck functor. We want like a commutation property between yeah, taking limits and colimits in the two variables, and assume that one, for every beta in J, the map F blank beta, which is a functor from E to Groth, actually lands into left exact things. And 2, for every alpha in E, F alpha blank from J to Groth actually lands in almost compact Grothendieck categories. And free, like base change condition, for every alpha to alpha prime in E and beta to beta prime in J, the square, F alpha beta, F alpha beta prime, blah, 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 which commutes, is horizontally right adjointable, which means that the horizontal maps admits right adjoint, and the canonical map that you have makes the diagonal commute. Yeah, then, sorry, like, I have to check because like it's a lot of conditions, and is it correct? Yes. Then let f alpha star be the colimit of f alpha beta, where beta is in J, and f star beta be the limit where alpha is in I of f alpha beta. Then the map f alpha star to f alpha prime star is left exact, so like the right thing that you will expect. And the converse, f star beta to f star beta prime, is almost compact. So like this tells you that if you have such, yeah, you can somehow pull out the limit or co-limit. And two, the functor from the colimit of f star beta, where beta is in J, to the limit for alpha in I of f alpha star is an equivalence. So a commutation rule. And yeah, 3 minutes, but I think I will stop here. So thank you.
All right. Thank you very much for the talk. Okay, so are there any questions for the speaker? Okay, if there are no questions, let me maybe say like a few words about this last proposition, because that was quite quick and like a lot of words. Maybe as a short slogan, somehow co-limits along left exact things stay left exact.
Yes.
Limits of almost compact or also compact things stay almost compact. Yes. So this is somehow the first part of this conclusion. And then if you have co-limits along left exact things commutes with limits along almost compact things. So yeah, I mean, there's this like right adjointability condition somehow, which tells you that this has some more compatibility, but basically that's somehow the idea. And this is just a sort of the technical thing that we will need later on, and which also explains maybe why this almost compactness is relevant, because it somehow tells you that you can commute some limits and co-limits. All right. Okay, then let us thank the speaker again. Thanks very much. Next time we will see Gustav talk on some more properties of Grothendieck Prestable categories. We will introduce a monoidal structure, and yeah, talk a bit more about limits, I believe. All right. Yes, then thank you very much and see you next week.